again, we have your expected value y2 given y1. So define a statistic for phi y1. So this statistic phi y1 is a function of the sufficient statistic for theta. Okay. So since our y2 is unbiased estimator, so our phi y1 is also unbiased estimator of theta. So given that your variance for phi y1 is less than y2, so we will find, so again, so you have your phi y1 is a function of the sufficient statistic for theta. So this one phi y1 is unbiased estimator of theta. And then this phi y1, the variance phi y1 is less than variance y2. So if our variance phi y1 is less than variance y2, that means phi y1 is uniformly minimum variance unbiased estimator. Okay, that is the theorem where we call this one as Rao-Blackwell theorem. Okay. Any response? Any comment?
Okay.
Boleh?
Yang variant Y2 tu memang sentiasa lebih besar
Okay. We will prove, dia tak sentiasa lebih besar. We will prove that variance phi y1 is less than variance y2. If your variance phi y1 is less than variance y2, then it fulfill to be uniformly minimum variance unbiased estimator. But if we prove, we show that variance phi y1 is greater than variance y2, so that it is not uniformly minimum variance unbiased estimator. Okay, the condition to be uniformly minimum variance unbiased estimator, your variance phi y1 here, okay, variance phi y1 must be less than variance y2.
Okay.
Okay, so nanti we will relate to the example. So example nanti lebih clear lah. So this is we call as Rao-Blackwell theorem. Actually it's a continuation from Kramer-Rao. Okay, the same person, Rao. Okay, so but another author lah, which is Blackwell. So we have two person, Rao and Blackwell, for this theorem. So that's why we call Rao-Blackwell theorem. Okay. Okay, so this theorem again, Rao-Blackwell tells us that if a sufficient statistic exists for a parameter, so in order to find unbiased minimum variance estimator, we should restrict the search to function of the sufficient statistic. The meaning for this one, that means if we have the PDF function or probability mass function, first we find the sufficient statistic. Okay, in order for you to find unbiased minimum variance estimator, you only focus to the function of the sufficient statistic. Let's say our sufficient statistic is x bar. Okay, so function of the sufficient statistic, let's say summation si over n, summation si is a function of the sufficient statistic. So that means it's related. So just focus on the function of the sufficient statistic in order for you to find unbiased minimum variance estimator. Okay. But if we begin our search with unbiased estimator y2, that means we prove that expected value of y2 is equals to theta, where your y2 is not a function of the sufficient statistic y1 alone. We can improve on this estimator by finding the conditional distribution or conditional expectation. Expected value of y2 given y1, which is equals to phi y1, so that your phi y1 is an unbiased estimator with smaller variance than y2. Okay, so let's say we start with y2. Okay, y2 is not a function of the sufficient statistic y1 alone, but y2 is unbiased estimator. Unbiased, that means expected value of y2 is equals to theta. So we need to improve this one. So by compute your conditional expectation. So expected value of y2 given y1. So we have phi y1. Okay. So phi y1 now is unbiased estimator. So we will prove that variance phi y1 less than variance y2. Then your phi y1 is unbiased minimum variance estimator. Okay, itu dia punya konsep. But if we start with sufficient statistic, that's meant to find unbiased minimum variance estimator, only focus on the function of the sufficient statistic. Okay, this one, that's mean the question find sufficient statistic. Yang first theorem ni. Okay, And then to find your unbiased minimum variance estimator, we just focus on the function of the sufficient statistic. But second part, okay, if we begin with unbiased estimator, we prove the expected value of y2 is equals to theta. So we try to improve by compute the conditional expectation. So conditional expectation, we have phi y1. So phi y1 is unbiased estimator with smaller variance, then phi y1 is unbiased minimum variance estimator. So itu dia punya theorem, Rao-Blackwell theorem. Okay. So let's say we refer to the example, sorry. Okay, we have another definition. Okay. So again, this one is also related to MLE. MLE, okay. If we compute the MLE, normally if your MLE exists, so your MLE also must be a function of sufficient statistic. The same example, let's say we take X bar. Okay. X bar is your MLE. Your sufficient statistic is summation Xi. So since your X bar can be written as summation Xi over N, so that's mean your MLE X bar is a function of the sufficient statistic. Okay, itu maksud that definition note. Okay. Ini dia punya theorem dia. Okay, refer to this theorem. Jadi theorem 2.3 So again, we have a random sample. We have sufficient statistic. Okay, sufficient statistic. So if a sufficient statistic y1 for theta exists, and then a maximum likelihood estimator theta head of theta is also exists, then theta head is a function of sufficient statistic. So that's means if we have a sufficient statistic y1 for theta exists, and then we also find the MLE, maximum likelihood estimator for theta head, is also exists, then theta head is a function of sufficient statistic. This theorem relate to this proving. Okay, let's say we have a PDF of sufficient statistic and function G. Okay, because in this case, the way we want to construct the sufficient statistic, we need to construct the likelihood function. Okay, likelihood function, that's mean your joint PDF. So based on your factorization theorem, we can split into two parts here. Okay, function G and also function H. So since your function H does not depend upon theta, so function G, U1, S1, S2, Sn is a sufficient statistic for theta. Okay, so thus your likelihood L and G as a function of theta are maximized simultaneously. Okay. So since there is one and only one value of theta that maximizes L, and hence for your function G, so that value of theta must be also the function of your sufficient statistic. So that's why we call that MLE theta head is a function of the sufficient statistic. Okay, itu based on definition, based on definition for sufficiency, because we need to construct the likelihood function. So construct the likelihood function, we construct the joint PDF. So once we have the joint PDF, for based on factorization theorem, we can split into two. First part contain data, second part does not contain data. So it is the same or the similar way we want to construct to find the MLE. Okay, so that's why this one highlight that only one value of theta maximize L and also maximize your function G. So that's why your theta is a function of sufficient statistic. Okay, that is the theorem. Boleh? Okay so far?
Okay, sekarang okay.
Penatlah pula. Okay, sekejap. Boleh. Okay, we refer to one example. Okay, example 2.4. So this one is in your notes. So this one is Poisson distribution. Okay. So we want to show that MLE. So MLE for Poisson distribution is a function of the sufficient statistic. Okay, so this is your probability mass function. Okay, we have exponential negative lambda to the power x divided by x factorial. So to construct your MLE, so first you construct your likelihood function. Okay, join PDF. So that's mean we have exponential negative lambda to x1 over x1 factorial, exponential negative lambda x2 over x2 factorial up to xn. So we have simplify, we have this value. Okay, exponential negative, sorry, ini dah tukar theta pula. Okay, you also tukar exponential negative theta exponential negative theta to the power x divided by x factorial. So we have here is exponential to the power negative n theta over summation si over product si factorial. Okay, so we find the MLE. So we take ln, so n theta, negative n theta plus summation si. Okay, so z equals to 0, differentiate with respect to theta. Z equals to 0, so we have x bar is the MLE. Okay, so the same thing. Now, second step, we find the sufficient statistic. Okay, sufficient statistic, that's mean the same thing. You already have your joint PDF. So joint PDF, split into two parts. Okay, so we have exponential negative n theta to the power summation si, and the other one is 1 over product si factorial. So that's mean your g, okay, function g theta is just your exponential negative n theta, so theta summation xi. And then your hx is 1 over product xi factorial, which is does not depend upon theta. So based on factorization theorem, your t, okay, function t ni, is summation si is a sufficient statistic. Okay. So note that since our x bar, okay, x bar can be written as summation si over n, then the MLE is a function of the sufficient statistic.